Hi, my name is Manish Gupta, and in this video, I'm going to talk about Reveal, which is a retrieval augmented model for visual and language kind of scenarios, multimodal scenarios. It basically is for multi-source, multimodal scenarios. So let's see how it works. Um, as I mentioned, Reveal is essentially a retrieval augmentation with multi-source, multimodal knowledge memory. So the use case is as follows. You essentially, let's say you have a query, this children's icon toy was named after whom, right? And essentially, you have an image in place. So to be able to answer this query, what you could do is to leverage several documents on the web or any other multimodal knowledge sources. So for example, these are some documents coming in from Wiki image text corpus, right? It has basically image as well as contextual paragraph from Wikipedia. There is another entry coming in here from Wikidata. There are some examples coming here from VQA, visual question answering dataset. Using these, you could fuse all of this knowledge and then somehow generate really good output that the mask should really be President Theodore Roosevelt, who refused to kill a black bear in a hunt, and therefore, teddy bears are named after him. Okay. So this is the basic idea behind Reveal. Reveal consists of four important parts: memory, encoder, retriever, and generator, which are also typically there in every retrieval augmentation kind of a model, right? However, the interesting part here is that the sources, first of all, there are multiple sources for memory, knowledge memory, and then they are also multimodal in nature. As I mentioned also in this example, in fact, there is a Wikipedia image text as a source, which has Wikipedia images, captions, as well as contextualized paragraphs, right? It also uses conceptual CC12M as a source, which has web images and alt text captions, catering to a whole bunch of tail entities as well. It has this visual question answering data set as an input, which merges all, where all question answer pairs for the same image are merged into a single passage. And it also takes triplets from Wikidata as a part of its memory. Okay. So the idea is that in an asynchronous way, you basically take the data from several knowledge sources and update your knowledge memory, or you store that stuff as in knowledge memory as key value pairs, where keys are essentially embeddings and memory are detailed text pieces or detailed image, representations of the images. Um, so this part of the memory is maintained in an asynchronous manner, right? When a query comes in, and the query could also be multimodal in nature, so it can actually have an image and text piece as well. The query comes in, you essentially encode the query using a visual linguistic encoder, the same encoder that you also use to actually encode the visual linguistic pieces into the knowledge memory. Use the same encoder, and then you find k nearest keys from the memory. You take those k nearest knowledge pieces from the memory and then appropriately fuse the information from the knowledge pieces and the query which has come in, and then finally use a decoder so as to output the final result, final answers. Okay, so essentially it is a language model. After all, there is an encoder and there is a decoder. So there is a encoder decoder language model, and then it's all supported by an external memory, which is basically multimodal, multi-source in nature. Okay? So thus there are four parts: memory, which encodes knowledge entries from different corpus into a unified key value kind of a framework; encoder, which basically encodes a multimodal input into a sequence of token embeddings, and also a summarized query embedding, as we'll see more in detail in the next slide. There is a retriever, which basically tries to find top k similar keys from the knowledge memory and returns their pre-computed in-memory value embeddings. And also, for some parts of them, it also re-encodes them, as we'll see again in detail in the next slide. And then there is a generator, which basically fuses first the top k knowledge pieces with the query embeddings via this attentive knowledge fusion layer, and then also uses all of this to decode the final output. Right? All of these four parts, the knowledge memory, the encoder, the retriever, and the final decoder, they are all pre-trained end to end. The nice part about Reveal is that Reveal is a very recent paper. It's a CVPR 2023 paper, and essentially it has basically shown state of the art on visual question answering and image captioning. So let's look at different parts, the four different parts of Reveal in detail. Here is the encoder and here is the memory, right? So as you see in the memory, you have data coming from various sources: Wikipedia image text corpus, Wikidata corpus, visual question answering corpus, You take all of those memory pieces and encode them using a base visual linguistic encoder. You also use the same visual linguistic encoder to encode query at runtime. So on the left side is basically a multimodal query coming at runtime. So as to basically encode these two pieces, encode whether a query at the runtime, multimodal query at the runtime, or multimodal knowledge pieces, right? You use the same visual linguistic encoder, and that's basically a combination of VIT, visual encoder, and for text there's a lower T5 encoder. Lower T5 just means the first few layers of the T5 encoder, right? So as to bring them into the same embedding space, you essentially apply a projection on the VIT output. Right? Now, after you're done with the base VL encoder, you essentially take the CLS token from an upper T5 model, so as to essentially get the query embedding, or also you do the same thing on the memory side, so as to get the key embedding, right? So essentially, again, this query head or the key head are both basically T5 encoder, the upper layers of the T5 encoder. Okay. So that's that. And now, of course, when you have these image pieces and the text pieces, you first get multiple token embedding representation for them, and those are summarized using the query head, which is basically the CLS token from or rather a processed CLS token from the upper layers of the T5 model. Okay. So memory, well, the memory is updated. So once you essentially, get the key essentially for the memory, you also get the value part. So the value part essentially is, these various text pieces and the image pieces. You actually summarize them. So the way you summarize them is basically you take those embeddings using the visual linguistic encoder, and you have a entire sequence of token embeddings. You take the sequence of token embeddings, which can be variable in nature because, for the same entity, rice, for example, you may have so many images and so many text pieces. Now you can have that variable in size, but then you all convert them to 32 tokens, essentially using the perceiver architecture. So that basically gives you a fixed size value representation, which you store in the memory. So the memory, of course, contains keys and values, where keys are just a single key embedding to represent the entity, and the values are essentially 32 different tokens representing the image and the text information related to the entity, right? So now you store this memory, unified memory, one for every source. So there is the memory for maybe the VQA dataset, memory for Wikipedia image text corpus, and so on, right? So you keep these entities across sources separately into your unified memory. And of course, inside each of those sources, you have key value pairs per entity. Okay. So the memory is updated asynchronously every 10,000 steps, every 1,000 training steps. Every 1,000 pre-training steps, you essentially update the memory. Now, the next part in this architecture is the retriever. So essentially, when a query comes in, of course, you encode the query using your base VL encoder, and you have a query representation coming in from the upper layers of the T5 encoder. Right? So your T5 encoding is basically done here. Now, what you do is to take the query and then essentially, given the query, you try to figure out which of the knowledge sources will be useful and important, right? So that's basically just a simple single dense layer, which basically figures out this corpus gating. Essentially just tells you the probability with which you can find the information to be able to answer this query across different knowledge sources. Now, you essentially take this query also, of course, so as to do maximum inner product search onto this memory or the index that you have built, and essentially try to retrieve the top K memories that match with the query, right? So you take the top K memories which match with the query, and that's basically MIPS maximum inner product search kind of a problem where where you have query and the memory keys playing the role. Okay. Now, when you retrieve the relevant memory pieces from this relevant knowledge pieces from this memory, you essentially take most of them as it is, but 10% of them you re-encode them so as to essentially have an end-to-end training of the encoders also. So you re-encode them, right? So so that's that. Now, the last part in this particular architecture is the generator part. So essentially, as you see in the generator, you have your top K retrieved knowledge pieces, which is a combination of both the actual in-memory knowledge as well as the re-encoded knowledge. And then you combine this information along with the query information which is coming in so as to have attentive knowledge fusion. So the idea in the attentive knowledge fusion guy is basically you incorporate the retriever score also. So far, you've basically just taken the retrieved knowledge pieces, but then you also bring in the retriever knowledge score as a prior for calculating the cross attention. So you're calculating the cross attention here in the attentive knowledge fusion, where you have the query coming in and the retrieved knowledge, but then while computing this cross attention, you also bring in this knowledge retriever score, which basically also ensures that you have an end-to-end training rather than just using the retriever score to get a discrete list of top few. Well, you also retain the score so as to have an end-to-end pre-training going on. Okay. After this attentive knowledge fusion is done, the T5 decoder text takes over and essentially generates the final output. So that's the overall architecture. Now, how is the pre-training done? Well, the pre-training is basically done using a very large 1.3 billion image caption pair corpus from, called as the web image text corpus. The pre-training is actually done using text generation. So as input, you pass in the image and a part of the caption as prefix. And at the output, you essentially expect the entire caption to be generated. Okay, so that's how you do an end-to-end pre-training of the 4 pieces of the entire reveal architecture: the encoder, memory, retriever, and generator. Right, so all of those. Now the retriever cannot be a dump retriever, otherwise the retrievals will be very bad in the beginning. So therefore, you avoid the cold start by warm starting the retriever. So to warm start the retriever, in fact, the way the pre-training is done is that you first pre-train the retriever and then you do the entire, the entire language model or the reveal model pre-training, right? So the way the retriever is pre-trained or warm started is by actually using the Wikipedia image text corpus. This corpus actually has 3 parts for every entry. There is an image, there is a caption, there's a Wikipedia paragraph. So you basically, for the retriever, you essentially say that, hey, I'm going to use the image and the Wikipedia paragraph as the query, and I'm going to retrieve the image, the knowledge pieces, the image and the caption and the Wikipedia paragraph, all of that from the memory. Okay. So, and you basically train the retriever. The retriever, remember, contains the T5 encoder. So you train the retriever using the contrastive laws, basically saying the retriever should basically favor, if there are, let's say, 10,000 knowledge pieces, many of them are negative, one of them is positive. So the retriever should be able to retrieve the positive guy rather than, and ignore all the negative guys, right? So that's basically the contrastive loss, which is used to warm start the retriever. So as part of pre-training, you first pre-train the retriever, and then you pre-train the entire reveal model. Right, so that's basically that. And the reveal model is sort of pre-trained using 10 knowledge pieces. So when you're retrieving the top K knowledge, you retrieve 10 knowledge pieces. They basically train 3 different sizes of reveal models: reveal base, reveal large, and reveal. The reveal model itself is the largest one and essentially is 2 billion parameters in size. The online retrieval, the memory is basically distributed in nature, and therefore you do distributed online retrieval using TPU-KNN method, which basically means that the entire memory is sort of split and stored across devices, and then the retrieval also happens first locally across those devices, and then there's the global top K, which is computed. All of these pieces in the entire architecture are appropriately initialized using transfer learning. So for example, the visual linguistic encoder is initialized using a T5 model. The attention fusion layers as well as the upper T5 models are, of course, initialized using the upper layers of the T5 pre-trained T5 encoder model. Okay. At fine-tune time, you freeze the VL encoder. You basically do not update the VL encoder at all. And you use K equal to 50 different retrievals. Because that's the difference between the fine-tune and the pre-training part. Now, they experiment with the several VQA datasets or the 2 VQA datasets, the OKVQA and a specific subset of OKVQA called as the AVQA. They also experiment with 2 image captioning datasets, MS-COCO and NoCaps. Right? So what you observe is that reveal architecture, of course, is not just better compared to the older usual architectures where there were no knowledge sources being used, but also those architectures where different kinds of knowledge sources are being used, and more recent architectures where, like CAT, which I covered in the previous video, right, where essentially you're using Wikidata and frozen GPT-3 kind of knowledge sources, right? So as you see, Reveal is way better compared to these previously proposed architectures. It is actually better even on this specific dataset OKVQA compared to any of these earlier architectures, right? Earlier multimodal architectures as well. Right? Now, here is an example, of course, to show what kind of retrievals do you get from the reveal architecture. So if there's an input image, there is an umbrella, right? And what flag is on the umbrella is the question. Now, these are the 2 retrieved, knowledge pieces. As you see, this is the Wikipedia page with the Union Jack flag, right? And there is basically also other umbrellas with the same, thing talking about London as a caption, right? So essentially, therefore, the ground truth prediction, the ground truth is of course England Union Jack, and the prediction is Union Jack, which is very accurate thanks to the multimodal knowledge memory and knowledge sources which Reveal has access to. Of course, on image captioning datasets also, you can observe, as you can observe, Reveal actually comes up with a really high CIDR score, much better than existing baselines. Okay, to summarize in this video, I talked about the Reveal model, which is basically retrieval-augmented visual language model. It depends on 4 important components: the encoder, retriever, memory, and generator, which are all end-to-end pre-trained, right? And it helped establish state-of-the-art on visual question answering and image captioning datasets. Okay, so that's all. That's all. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.